Next we will consider the case where x and y are jointly continuous. Okay, so, the discrete case we are done, we are going to go consider the jointly continuous case. In these two special cases you get nice expressions, otherwise you have no other option. If so, if you do not have, if you have some crazy random variables x y with some very bizarre CDF, you have to simply look at the probability mass below this line, there is no simple expression for it, right. But in the case when x and y are discrete or x and y are jointly continuous, you will get some nice formula, and these are the cases of maximum applicability in engineering. Okay, so, these expressions are useful to know and useful in practice as well. Okay. Okay, so, let us say x and y. So, we finish the assume now, assume next that x and y are jointly continuous if they are jointly continuous, I have a joint density, joint PDF with joint PDF f x y, which is given to you. Now, I want the density of, so I actually want, let me say I will start out by saying I just want the CDF of z, right. What we will see is that z will also actually be a continuous random variable. So, not only, so we can actually get its PDF as well, right. So, this is what we want. So, we will write f z of little z as, so this is probability of big Z less than or equal to little z. This is simply, so you know that for any, so you know that the probability of any Borel set is given by the integral of the joint PDF, right. So, I am now seeking out, so this is what I want, the probability of this set is what I want, right, the set that lies below the line, and that is a Borel set you can show. So, the probability of lying in that Borel set will be the integral over that set of little f x y, right. So, this will just be integral x y such that x plus y less than or equal to z f x y of x y dy dx or dx dy, does not matter, right. This you agree, this is Radon-Nikodym actually, right. Okay, so, now this integral, so after all, so if you write this as a double integral on R2, this will become integral minus infinity integral minus infinity z minus x f x y of x y dy dx. So, what I am doing is I am first integrating y out. So, I am doing, so if you look at this figure, I am integrating from y from minus infinity to z minus x, right. I am integrating along the y first and then integrating x from minus infinity to infinity, right. That is what this is, right, this integral is. Okay. Okay, so that is it actually, I mean if this is all there is. So, you know the joint density, you integrate it, this is an integral you can do, right, and what you will be left with. So, if you do the first integral, you will be left with something that is a function of z and x, and then x will also get out when you integrate the second time, then you will be left with some function of z. So, this is all there is, okay. But it turns out this can be simplified a little if you put So, conceptually it is over, but if you put, let me do this right, if you put t equal to x plus y, then this simplifies a little bit and gives you so minus infinity z, well okay, let me just minus infinity integral minus infinity z. So, I am just now I have gotten rid of z minus x is, I have put x, z minus x is equal to well I have put x, I have put t equal to x plus y, which means my y is equal to t minus x, right, y is equal to t minus x. So, I will have f x comma y of x comma t minus x, right, y is equal to t minus x, and I have dy is simply dt now, right. So, I will have dx dt, is that fine? No, dt dx I think. So, I am integrating this is the x integral, is not it? Yeah. So, dt dx, correct. This is just a substitution in the integral. Okay, good. Okay, so now this guy is non negative, all right. So, I can in fact there is no harm in interchanging the order of integration, okay. That is always valid if you have a non negative argument. So, this you can write as integral minus infinity z integral minus infinity infinity, this is also these two are equal, okay. Integral f x comma y of x comma t minus x. This guy, no I think so, no now my variable is t, isn't it. So, when my so I have gotten rid of y, right. So, y was going from minus infinity to z minus x, now my t is going from minus infinity to z, I think that makes sense, right. So, I have gotten rid of y. So, this is now I have dx dt, okay. I have just flipped the two integrals, which I can do because my integrand is non negative, okay. So, why did I do that? If you look at this integral, so if you look at this bit, okay, so that is getting rid of x, right, I am integrating x out. So, what remains will be a function of t, right. So, I will have something that looks like a density, right. So, this will be some non negative measurable function of t, and I am saying that the CDF can be written as integral minus infinity to z some function of t dt, which means this guy must be the density of z, right. So, this guy must be the density of z, which automatically proves that z must be a continuous random variable, correct. Okay, great. So, which means if you give me the joint density, I can easily find the density of z by evaluating this one integral, right. I do not have to in the integral outside is simply getting the CDF from the PDF, right. So, I can write thus. So, thus f z of little z is integral minus infinity infinity f x comma y of x comma little z minus x dx. So, you give me the joint density, I will find the density of the sum z, okay. This is the formula for that, and it is always a continuous random variable. If x and y are jointly continuous, z is always continuous random variable. And then you say in particular if x and y are independent, you will get f z of little z is equal to integral minus infinity infinity. I know that almost everywhere my density will joint density will product out into product of the marginal densities. So, I will get f x of x f y of z minus x d x. Okay. This is a convolution also, right. This is a convolution of. So, this is written as. So, you can write this as f z is equal to f x convolution f y, right. So, if x and y are independent jointly continuous random variables, then you get this formula. Now, you know that if I see x and y are independent and marginally continuous, it is automatically true that they are so it is jointly continuous, right. So, actually, so if x and y are independent random variables with densities x and y, right, you can always use this expression. Is this clear? So, if you have good practice in convolution, you can do a lot of examples like this, right. You take if x is some exponential and y is some independent Gaussian, you can convolve exponential and Gaussian and to say what the sum will look like, right. It will not be pretty, right, but in some cases you get nice answers, right. So, one such example you can show is if you take x as a Gaussian random variable with parameter mu 1 and sigma 1 and x y as an independent Gaussian with parameter mu 1 and mu 1 and mu 2 and sigma 2, then the sum will have parameters, sum will also be Gaussian, will have and it will have parameters mu 1 plus mu 2 and the sigma will be square root of sigma 1 square plus sigma 2 square. Okay, you can show it explicitly by doing this convolution. It will not be pretty in the beginning, but you can figure it out, right. You can convolve and figure it out. So, that is one thing you can do as a homework. See, eventually that is not how we will do it. So, you know that convolution is not cool, right, it is very ugly, right. So, normally what do people do when you want to convolve two things? You take your favorite transform Laplace or Fourier, multiply the transforms, right, and invert back. So, that is what we will do eventually, but for now we have not gone there. So, you can convolve for now, right. So, if you try the Gaussian example with different parameters, it will probably take you about half an hour to 40 minutes to actually do the integration, okay. But of course, if you use transforms, it is a lot easier, right, which we will get to later. So, let me do, shall I do an example? I will do an example. Example. So, let us say x 1 and x 2 are independent exponential random variables with parameters lambda 1. So, let us say mu 1 and mu 2. And z is equal to x 1 plus x 2. Now, f z of little z is given by integral 0 to. So, these PDFs are known, right. So, f x I of little x will be mu I e power minus mu I x, right. So, the individual CDFs are known, PDFs are known to you. So, and for this you will take integral 0 to z, because that is where both densities are non-zero. You will get mu 1 e power minus mu 1 x, mu 2 e power minus mu 2 z minus x dx, isn't it? Dx. So, which is equal to mu 1 mu 2 e power minus, well, e power minus mu 2 z, right, mu 2 z times integral 0 to z e power mu 2 minus mu 1 times x dx. Okay. Fine, just doing the convolution. So, in this case, if so, now you have two cases, right. It may be that mu 1 and mu 2 are equal, right. In this case, this whole thing will become e power 0, which is 1. So, the integral will simply be integral 1 dx will be z, right. So, in that case you will get mu square z e power minus mu z, right, if mu and mu 2 are equal to mu, and if they are different, this you have to integrate this out. Okay. So, you get two different forms. So, this will be equal to mu 1 mu 2 by mu 2 minus mu 1 e power minus mu 1 z minus e power minus mu 2 z, all that. This is true if mu 1 is not equal to mu 2, and this will be equal to mu squared z e power minus mu z if mu 1 equal to mu 2 equal to some mu. Okay. So, if you had the parameters were the same, then this will be the PDF. It will look like z e power minus z if mu equal to 1, right. So, this particular, this is called Erlang of second order Erlang 2. So, if you sum two independent and identically distributed exponential random variables, you get a what is known as an Erlang 2 distribution. Okay. And if you do this n times, you will get an Erlang n distribution that will look like mu power n z power n minus 1 e power minus mu z. I think there is an n factorial or n minus 1 factorial in the denominator. Okay. And in the case when the parameters are different, you get something, right. It is not some well known, this is not some well known distribution. This is a class, this is one of the classical well studied distributions. Because Erlang has lots of applications in calculating switch blocking probabilities in telephony and all, call blocking probabilities in telephony. Good. So, any questions on this? So, the other example, so the homework example I was saying was that so if x 1 is Gaussian with parameters mu and mu 1 and sigma 1 squared, right, we wrote down the expression for this, right, e power minus x minus mu whole square over 2 sigma squared and so on. So, and x 2 independent with parameters n mu 2 sigma 2 squared and they are independent, then x 1 plus x 2 is also Gaussian with parameters mu 1 plus mu 2 and sigma 1 square plus sigma 2 square. No, I am writing squares here, no? Yeah, so your sigma will be the square root of sigma 1 square plus square root 1 square. Okay. So, I am writing the what we will interpret as the variance, not the standard deviation. Okay. Okay, good. So, this is this you will show. Okay. Actually, now, yeah, if you try and show it now, it will be a very ugly exercise, but you should probably do it just to convince yourself that when you do it in a easier way later with transforms, you will have a much easier time. Okay. So, here this is a very fundamental property of the Gaussian distribution. This is one of the properties, it is one of the two properties that makes the Gaussian distribution in some sense the queen of all these continuous random variables, right. So, if you add any number of independent Gaussian random variables, you get another Gaussian random variables and the parameters also simply add. Okay. So, even if you add n of them independent random variables, you will get another Gaussian. Okay. So, it is a stable, distribution under addition. Okay. So, in the discrete world you saw Poisson was stable also, right. So, in the continuous world this is one example of a sum stable distribution, this is stable under summation. So, that is one of the reasons why this Gaussian is so important. Okay. And the other reason is central limit theorem, which says that if you keep adding a lot of independent random variables which are not even Gaussian, the sum will look approximately like a Gaussian. Okay. So, this is a central limit theorem is something we will do towards the very end of the class, okay, in proper detail, but before that we have a lot of ground to cover. So, this I have not proven because it is not because it is difficult, because it is messy, okay, and we will do it in a more elegant way later. Okay. Any questions? Okay, so if there are no more questions, I will stop here.